modeling process, Mark Hornick at Oracle. Mark, I personally don't think you need a big intro, my friend. I think you are awesome. We get to work with Mark a lot, and he's part of the community as well. So lots of cool things coming out of machine learning. Mark, I'm not going to go any further, mate. I'm going to let you take it away.
All right. Well, thank you so much, Abby. Certainly appreciate that. That's great. As far as, a fun fact, during the pandemic that we're looking for alternative things to do. And so when I was a kid, I used to have a garden. So this past year, we actually built a raised bed garden and have been growing banana peppers like crazy and pickling those, and also tomatoes. So it's been quite a good green thumb year for us. So that's exciting on that front. But in terms of automating the machine learning modeling process, so automation is often a key component to increase productivity and reduce cost. And so in this session, automating the machine learning modeling process using Oracle Machine Learning, we're going to look at some of the challenges confronting users of machine learning and some new features of Oracle Machine Learning for addressing those challenges. As Abby said, I'm Mark Hornick, Senior Director for Oracle Machine Learning Product Management. Lead the team for that. I've been with Oracle for a good number of years, and we continue to add new features to Autonomous Database and Oracle Database in the machine learning front. So let's start with the whole data scientist question, right? We demand a lot of our data scientists, and depending on who you ask, you'll get a range of responses as to what skills data scientists must have. Now, here are just a few of 207 million pieces of advice found with this Google search. Some skills fall into the category of perhaps hard skills, like programming, as with R or Python, data visualization, how to present data and results in a meaningful way, or even data wrangling, how to manipulate data and prepare data for machine learning modeling. And of course, there are some of the softer skills, like intellectual curiosity, that involve, do you have enough interest to pursue novel paths and not settle for the first result that you got? Communication and storytelling, how to effectively convey machine learning results in an intuitive and easily digestible way. We've got to communicate to business decision makers and not just present them with hard, cold data at the end, right? And then collaboration, working with people in diverse roles and with diverse skill sets. You've got domain experts, developers, and citizen data scientists, and they all bring something different to the table. Now, while common threads exist across skill sets, as shown here, we're going to focus on the thread involving machine learning, the process techniques and algorithms. And we know that data scientists and those with broader machine learning skills are in high demand, and that business solutions increasingly rely on machine learning to meet rapid development cycles. But we can use automation through OML to support data scientists while also enabling non-experts to get greater insight from their data. That's what we hope to share with you today. So, let's consider what the automation challenges are using the CRISP-DM process, the cross-industry standard process for data mining. So, since we're talking about automation, it should be clear that some of these steps would be difficult to automate, if not impossible. For example, business understanding and data understanding rely on human expertise to identify business problems and the data available to the organization, as well as data from external sources. Now, if we move on to data preparation, steps can be automated, but there's still a significant amount of domain expertise required. On the one side, you've got algorithms that require data to be one-hot encoded, normalized, or binned prior to modeling. And this is pretty straightforward to automate, right? You can even go as far as to do automation of exploring the interaction terms. But a more interesting and perhaps useful case is in the area of derived variables, where we have the need for domain expertise to really ferret out the subtle patterns and relationships. And this can be as simple as mapping synonymous values like maybe MA, Mass, and Massachusetts as the same state. But a more interesting and greater challenge is coming up with an effective marker for perhaps defining a churning customer that offers sufficient lead time to avoid losing customers. So defining these truly creative derived variables is not really a good candidate for automation, at least not today. And as we'll discuss here, the modeling process is ripe for automation. And modeling is largely a well-defined and highly iterative activity, even if viewed by some as an art and complex by others. But through automation, we can really increase data scientists' productivity while helping non-experts produce reasonable models. Now, the evaluation phase actually requires judgments based on business understanding. For example, are the success criteria met? Will business objectives be achieved? In our customer churn example, will we be able to reduce churn by 30%? So the evaluation phase isn't necessarily a good candidate for automation. We can also automate aspects of the deployment phase, making it easier to deploy, monitor, and update models for use in applications and dashboards. So in this presentation, we're going to focus on the modeling process. You have multiple algorithms to choose from. And for classification in Oracle Machine Learning, these range from decision tree to neural network. But the questions are, which of these should be tried and which is actually best? So we typically start with one algorithm. We'll build a model and tune it to hopefully improve model quality. Of course, each algorithm has its own settings, or what we call hyperparameters, and these need to be adjusted. Here, we're showing those for support vector machine. And we then, having built the model, we're going to compare each new model against the previous ones, selecting the best current model. And then we're going to repeat this process with the next algorithm, right? But we may also have to adjust our pipeline to introduce supplemental data or transformations and try these new data sets with each algorithm and settings combination. And this iterative and trial and error approach is expensive, both in terms of time and compute resources. So it requires that you really understand how to tune each type of model, unless you're up for a grid search, which is also called exhaustive search and can be rather compute intensive, not to mention taking a lot of time. So this motivates our desire to automate the modeling process. What are some of the pain points with traditional machine learning? Well, they include the need to meet rapid model development cycles and a process that can be complex and highly iterative. There's also a need, as we discussed, to understand the individual machine learning algorithms in enough detail to get high quality models. And due to the wide range of algorithms, the modeling process can be time intensive to explore the space of not only the candidate algorithms, but also their corresponding hyperparameters. Now, broadly speaking, solutions to these pain points include introducing an efficient machine learning pipeline to address the need for rapid model development. And this can be done if we can eliminate repetitive tasks through automation. And of course, the goal is to increase model quality and user productivity. Now, to the extent possible, let's also apply machine learning to the machine learning process itself to allow us to automatically zero in on the right algorithm and the right features, as well as the hyperparameters necessary to build high-quality models. Now, such capabilities help to make machine learning accessible to a broader audience while reducing the time required to get the desired results. So this is where Oracle Labs comes into the picture with their AutoML solution, Automated Machine Learning, to provide an efficient machine learning pipeline. What do we mean by an efficient machine learning pipeline? Well, we define this as one that obtains an accurate model in a short period of time. Oracle Labs provides a novel iteration-free AutoML pipeline, and this means that it eliminates the need to repeatedly iterate over various pipeline configurations, which configuration consists of the algorithm, data, and hyperparameters. In this approach, each pipeline stage makes decisions based on meta-learned proxy models that can predict candidate pipeline configuration performance before actually building the full final model. And this way, only the best candidate pipelines are built and tuned. And this achieves better results in a fraction of the time, especially when compared to some open source AutoML tools. Now, many state-of-the-art AutoML optimizers are iterative and need to evaluate a large number of pipeline combinations. And of course, this takes a long time, and it makes iterative pipelines impractical for large data sets with short time budgets. And they can also be relatively expensive, especially if paying for cloud compute resources. So the Oracle AutoML approach rapidly narrows the search space by doing one-pass pre-processing, algorithm selection, and algorithm-specific adaptive data reduction. The data reduction itself includes both row-wise and feature-wise dataset sampling, and it's followed by hyperparameter tuning. So although not all pipeline configurations are tried, AutoML reduces the risk of missing the optimal pipeline by meta-learning one proxy model per algorithm. And this allows more accurately predicting relative ranking between different pipeline configurations. These novel aspects of the Oracle AutoML approach allow it to be significantly faster and in most cases more predictive than other state-of-the-art AutoML approaches. This slide summarizes those research contributions. They include an iteration-free optimizer, proxy models, as we discussed, adaptive data reduction, and a parallel gradient descent hyperparameter optimizer. Now, the Oracle AutoML methodology supports both Oracle machine learning in database algorithms as exposed through OML for Pi, and the OCI data science use of select open source Python algorithms, and there are other uses of this technology as well. So this points to the flexibility of the technique and provides both database and open source users with powerful machine learning modeling automation. The proxy models we referred to a moment ago are built specific to the in-database algorithms and supported open source algorithms. So now we're going to turn our attention to the components of Oracle Machine Learning that leverage Oracle AutoML, namely the Oracle Machine Learning AutoML UI and Oracle Machine Learning for Python AutoML. So the Oracle Machine Learning AutoML UI is a no-code user interface supporting automated machine learning for both data scientist productivity and non-expert user access to powerful in-database algorithm. It accelerates machine learning projects by giving quick feedback on dataset suitability for producing useful models. And this alleviates much of the drudgery and pain points of the machine learning process. Oracle Machine Learning AutoML UI automates model building with minimal user input. You just specify the data and the target in what's called an experiment, and the tool does the rest. However, users can adjust some settings, such as the number of top models to select, the model selection metric, and even specific algorithms to consider if you want. As we're going to see soon, running an experiment shows incremental progress monitoring and produces the leaderboard of models and their corresponding performance. So with a single click, users can also generate editable starter notebooks. And these notebooks contain data selection, building the selected model, including the settings used to produce that model, so you get some transparency into what AutoML actually did, and scoring and evaluation code, all in Python using OML for Pi. You can build on this generated notebook to apply your own domain expertise to augment that solution. In addition, deploying models from the AutoML UI as REST endpoints to OML services takes just a few clicks. Scoring using these deployed models is optimized for streaming and real-time applications. So unlike other solutions that require provisioning a VM for 24/7 availability, OML services is included with Oracle Autonomous Database. So users are only paying for the additional compute when producing actual predictions. We'll say more about that a little bit later. So here's a quick overview of the experiment pipeline adapted from what we saw earlier, which consists of 5 principal steps. We start with a prepared data set, meaning that it has one record per case or example, has appropriate data types, and has a well-defined target. So with automated algorithm selection, the goal is to identify the in-database algorithms likely to achieve the highest model quality to predict this target. And using this approach called meta-learning, AutoML leverages machine learning itself to help find the best algorithm faster than with exhaustive search. Moving on to adaptive sampling, this identifies the right sample size for training data and adjusts for unbalanced data, such as when your target has perhaps few positive cases relative to the negative cases. With the automated feature selection, the goal is to denoise data by eliminating features that don't add value to the model. So by identifying the most predictive features and eliminating this noise, model accuracy can often be significantly improved, not to mention the side benefit of faster model building and scoring. It uses rankings that are based on algorithms such as minimum description length, MDL, random forest, GLM coefficients, correlation, as well as a combination of the four of these. It then tries subsets of the ranked attributes before picking the best subset. Next is automated model tuning. And so this tunes the algorithm hyperparameters and can significantly improve accuracy while avoiding manual or exhaustive search techniques. Finally, we've got a feature prediction impact, and this ranks the features that most influence predictions. And these are computed in an algorithm agnostic manner. So it means that these results aren't really specific to the type of algorithm that's used. Each final model produced per algorithm has its own feature rankings in the experiment. So now we'll have a demonstration of the Oracle Machine Learning AutoML user interface, which will also touch on OML Models UI and the generated OML for Pi notebook. Here, we're looking at the Oracle Machine Learning user interface on Autonomous Database. We'll start with the AutoML UI by clicking the AutoML icon under Quick Actions. On this screen, we have our listing of AutoML experiments, and one that we created earlier, wine cultivators, which we're going to recreate now. We'll call this experiment Wine Cultivators 2. We select the data we want from our database tables. We can search here for the schema OML user and the table name containing wine. The wine table contains data from the chemical analysis of wines grown by 3 cultivators in one region in Italy. The goal is to predict which cultivator produced the wine based on its chemical analysis. We then select our target column, what we're trying to predict, which is called target, namely the cultivator of the grapes. We can just start typing in the name to automatically filter columns. A case ID, or unique identifier, can be specified to enable greater repeatability. However, this dataset doesn't have such a case ID, so we'll just leave it blank. Notice that the prediction type is automatically set to classification. This is based on the target data type and number of distinct values. AutoML supports both classification and regression problems. Now you'll notice in the features section that statistics are available on our predictor and target columns. These are obtained from the database table statistics. We can see percent nulls, distinct values, min, max, mean, and standard deviation. Our target column is highlighted with this symbol, and we see that it has 3 distinct values. Let's look at some additional settings. We can select the maximum number of top models we would like to build, which is set to 5 by default. You can also set a maximum run duration to time limit the experiment runtime. If you don't enter a time, the experiment will be allowed to run for up to the default, which is 8 hours. If the limit is exceeded, the experiment will be stopped early, and you can view results up to that point. We can also specify the autonomous database service level. We'll choose high to enable parallelism and have the most possible CPUs working on the problem. We also have a range of model metrics to choose from for selecting the top models. Here, balanced accuracy is selected by default. There are multiple algorithms we can choose from. While all are selected by default, we may want to exclude certain algorithms. For example, to ensure that we have algorithms that offer transparency, like human understandable rules or feature coefficients. But we're going to leave all of the algorithms selected here. Now that our experiment is specified, we can start it by choosing one of two options, faster results or better accuracy. Faster results uses fewer pipeline combinations. Better accuracy uses a broader range of pipeline combinations. We'll go with better accuracy. So we're starting the experiment. It's now running, and we see the progress bar defining the workflow we introduced earlier. After an initialization phase, we have algorithm selection to decide which algorithms are predicted to give the best accuracy. Recall we asked for 5. We then have adaptive sampling and feature selection, followed by model tuning, and finally feature prediction impact. AutoML selected neural network and support vector machine with a linear kernel and a few other algorithms. We'll let that continue to run. If we scroll down to features, we see the algorithm agnostic ranking of predictors. This feature importance gives the overall level of sensitivity of predictors to the particular feature. And if we hover our cursor over the graph, we can view the importance value for a given feature. The value is in the range of 0 to 1, with values closer to 1 being more important. We see that the top features include flavonoids, color intensity, and proline. We're going to let this experiment continue to run, but I'd like to jump over to the experiment that's already completed. Let's open wine cultivators. To see the settings used in this experiment, we can expand experiment settings. Notice that the set of algorithms is just the default list. We can also edit the existing experiment by clicking Edit, and we'll get the same interface that we had earlier. Since this experiment completed, we can click on the Completed button to see its status. This experiment took 14 minutes to run. Notice that initialization has an information icon. We can click that and see that some algorithms were excluded because they don't support multi-class classification, like logistic regression. If there are other issues in the process, the green check mark will be replaced by warning or error icons with additional information. The model metrics chart that you see here depicts the best metric value over time as the experiment runs. It shows the improvement in the metric as the experiment progresses. The display name depends on the metric selected when we created the experiment. In the leaderboard, we see that neural network and SVM performed best, nearly perfect, for balanced accuracy. We can view additional metrics by clicking Metrics and selecting the ones we want. We can sort these by metrics as well. Now let's look at some of the model details. For the neural network model, we see the prediction impacts ranks proline, alcohol, and color intensity as the top predictors. We can also look at the details for the SVM model. Here we see that flavonoids, alcohol, and proline were chosen as the most predictive. The next thing we might want to do is to deploy our model. We renamed our neural network model to WineNN in this case. Model names are automatically generated, as you see here, and are somewhat cryptic, so we often choose to rename models. Let's rename our linear SVM model to Wine SVM Linear. From here, we'll deploy this model. The model name is pre-populated, and the URI is going to be Wine SVM LNR. The version is 1.0, the namespace is demo, and that we want to share this model with others. By just clicking OK, this model is now deployed to OML services. If we go to the Models interface, we have the list of models that are available to us, and we can see our Wine SVM model with a quick search. We can deploy models directly from this interface by selecting it and clicking Deploy. But we're going to focus on the models deployed directly from the experiment. Here you see that we have the Wine SVM linear deployment, that it's shared, and the remaining properties of the deployment. To see the model metadata, we click the name to get the JSON description of columns that are used, the output, and the labels, along with the model name. And clicking on the URI, we see the OpenAPI specification for this model. With this, we're now ready to use it as a REST endpoint through OML services. Let's go back to our experiment, the one we created. We see that it's completed. Now let's generate a notebook with code to build our neural network model. With the model selected, we click Create Notebook. And we'll call this Wine Neural Network. And now the code has been generated as a starter notebook for us to work with. We'll open that notebook. Let's do a quick search, and we see that we have the Wine Neural Network notebook. Clicking this, now it's loading the notebook itself. The first thing we'll want to do is to set our interpreter binding so that we're able to connect to the database. We'll choose the medium binding and save that. Now, if we run the first paragraph, we'll see the experiment metadata associated with this notebook. We have the experiment name, Wine Cultivators 2, the workspace, our project, and other properties. The next paragraph imports OML, and when this paragraph is run, it establishes a connection to the database for OML for Pi from the Python interpreter. Then the generated code lists the columns that were used to produce this model, the schema, and the table name. The generated code then forms a query and invokes OML sync to get a proxy object for this data in the variable build data. And in the result, we're looking at a few of the rows from that table. Next, there's some data preparation, like separating the predictors from the target, as is the Python convention. Next, we see the algorithm settings used by AutoML to produce the neural network and the code to build the neural network model itself. Here we see the model details with the settings that were used. Some global statistics, the attributes, and the topology and weights of the model. We'll score data using the predict function and compute the balanced accuracy score. That concludes our demonstration of Oracle Machine Learning AutoML UI. Okay, so hopefully that gave you a good idea of what Oracle Machine Learning AutoML UI is all about. And so the second component we're going to talk about is one that also supports AutoML, the Oracle Machine Learning for Python interface. So here's a brief introduction to OML for Pi first. OML for Pi leverages the database as a high-performance computing environment. It manipulates database tables and views through Pandas data frame proxy objects with overloaded functionality that's translated to SQL transparently behind the scenes. And you can invoke in-database scalable machine learning algorithms through a natural Python interface, as we just saw with the generated notebook. And on autonomous database, you can take advantage of optimizations such as autoscale. Now, users can create user-defined Python functions managed as scripts in the database, and Python objects themselves can also be stored in the database as opposed to being managed in flat files. These user-defined functions can be run in database environment-spawned Python engines, and through the use of multiple Python engines, users even benefit from system-provided data parallel or task parallel invocation from Python, REST, and SQL APIs. Results can contain both structured results, such as data frames, and image results, such as those produced using Matplotlib. Now, next is model explainability, or MLX. And this provides the model-agnostic identification of important features as they impact the model predictions. And then we have OML for Pi, of course, supporting automated machine learning, or AutoML. So let's dive into that a little bit further. In AutoML, OML for Pi, users have access to functions that support 3 key AutoML steps: automated algorithm selection, feature selection, and model tuning. And these are aligned with what we discussed earlier for the AutoML UI. There are also functions for model explainability, or MLX, included in OML for Pi, as well as a separate function for doing model selection that actually combines the algorithm selection with the model tuning. So let's have a demonstration of the AutoML functionality in OML for Pi. This is the Oracle Machine Learning User Interface on Autonomous Database. We'll click on the Notebooks quick action to take us to our list of notebooks. We'll open OML for Pi AutoML. In this notebook, we start with a markdown paragraph that introduces OML for Pi and the AutoML features we'll cover, namely automated algorithm selection, feature selection, and model tuning. First, we import packages and set display options. In this paragraph, we import pandas, OML, and the AutoML module of OML. Next, we create a dataset as a pandas data frame and load this into the database. For this demonstration, we use the wine dataset from scikit-learn, concatenating the predictors and the target to produce an integrated table. We use the function OML create to create a database table called wine. In the same paragraph, we print the shape of that dataset as well as the column data types, as you see here. Note that this just took the data from our Python environment and loaded it into our autonomous database, creating a table. We can look at some of the data in this table. Here are the first 20 rows retrieved via the proxy object wine. The first of our AutoML steps is algorithm selection. We can do this both for classification and regression. We'll mainly talk about the classification examples and highlight a few things for regression. First, we separate the predictors from the target. For classification, we're using the target column called target. And for regression, we'll predict the numeric column proline. The next step is algorithm selection. Here we create an algorithm selection object and specify the mining function as classification, along with the score metric, accuracy, and how much parallelism should be used. Next, we invoke select using our proxy object dataset and indicate how many of the top algorithms we'd like to have returned. In the result, SVM Gaussian was chosen as the best with 98% accuracy, followed by SVM linear and other algorithms. We did the same thing for regression and found that SVM Gaussian was again the top algorithm, but GLM Ridge came in a close second, followed by GLM and SVM linear. Next is automated feature selection. In this case, we're looking to find which features are most relevant for the algorithm just selected. We create a feature selection object, again indicating it's a classification problem, and our score metric is accuracy, and that we want to use parallelism. To reduce the set of columns, we invoke the reduce function, using the algorithm that we chose above, which is support vector machine. And we provide the data, both our predictors and target, which are proxy objects. With this, we see that the number of columns has been reduced from 13 to 9. In contrast, for regression, we see that the 13 predictors were also reduced to 9, but a different set of 9. Next is automated model tuning. We specify a model tuning object, indicate classification, and that we want parallelism. In the tune function, we specify the algorithm, the reduced set of predictors that we determined above, and our target. From this, we see the resulting support vector machine model and the hyperparameters that were used. Now, it's possible that a data scientist may have a different set of search space parameters in mind when working with a specific algorithm. In this case, the data scientist can specify a search space explicitly. Here, we're interested in using the random forest algorithm and providing a search space with the desired range of values for the sampling ratio, the number of trees, and impurity metric, both entropy and Gini. As before, we create a model tuning object and invoke tune, providing the algorithm RF for random forest, the input data, and the search space defined above. For regression, we did something similar, but used the neural network algorithm. Here you see options for the regularizer, activations, hidden layers, and nodes. Lastly, we'll talk about automated model selection, which combines both algorithm selection and hyperparameter tuning in a single step. After creating the model selection object, we invoke select, providing the original data, and that we want the top model to be returned, k is equal to 1, and that we'd like cross-validation with 2 folds. Here we see some of the resulting support vector machine model details. Similarly for regression. This completes our demonstration of OML for Pi, AutoML. All right, so again, you have the sense of what it's like to use the OML for Pi AutoML UI. And we're going to move on to a couple of other automation capabilities that we have with OML. So in addition to AutoML, the in-database algorithms actually support automation features when building models individually, as well as when scoring data. And these features aren't new necessarily. In fact, they've been around for the past several database releases, but are worth highlighting here in any case. And so these include algorithm-specific automatic data preparation, such as the one-hot coding of categorical variables and the binning or normalizing of numerical variables, integrated text mining through integration with Oracle Text, and this allows one or more columns to be identified as text, where features are automatically extracted and combined with others, structured data for model building. And then partition models, which automate the creation of an ensemble, where the model is built on each partition of data specified by one or more columns, but can be used and managed as a single top-level model. So we're going to explore these just a little bit further. For the in-database algorithms, OML automatically performs a select set of algorithm-specific data transformations when auto data prep is enabled. Because some data scientists may need full control over data preparation, they can turn this off, but it is enabled by default. Now, OML uses heuristics that address the common requirements of each algorithm, and the goal here is to produce a model with reasonable quality relative to the data that was provided, of course. These transformations and their associated metadata are bundled with the model for ease of scoring. And to the extent possible, OML provides insight into the model results and the model details in the original scale to help with model interpretation. We should note that auto data prep is supported across all the OML interfaces using in-database algorithms, and that includes the SQL, R, Python, and the AutoML UI and Oracle Data Miner tools. Auto data prep is enabled by default, but users can turn it on or off explicitly using, as in this case, the prep auto setting, as shown here in the SQL API. In the top example, we're building a classification model using SVM to predict whether a customer will buy travel insurance. And below, we see using that model in a SQL query to predict if a specific customer is likely to buy insurance. Batch scoring on a database table can be done just as easily, even as part of the table creation operation. Now, for integrated text mining, users can identify columns as text. Leveraging features of the Oracle Text component with Oracle Database, tokens and themes can be automatically extracted from the text and used by the in-database machine learning algorithms during model building. Models can be built using text content alone or in combination with other structured data that's present in the same table or view. Now, the text transformations extract these tokens and themes according to the user specification, and these are included with the model and automatically applied when making predictions. So this really simplifies the overall deployment process. In this example, the user creates a text policy using PL/SQL. There are a variety of Oracle text settings that users can specify with working with text, including things like stop words, lexers, stemming, among others. But the integrated text mining is also available through both the SQL, R, and Python APIs. So here, using Python through OML for Pi, the user specifies settings that include things such as the text policy name, and other related settings like the maximum number of features to include when building the model. And here we're limiting that to 3,000. In the CTX settings variable, we indicate that the column or columns should be treated as text. In this case, the comments column contains the text that we're going to analyze. And we're using the SVM algorithm to build the model and then score using the predict function. The last one we're going to talk about is the partitioned model feature, which automates a typical machine learning task for data scientists. Users can specify one or more columns to partition data and build models on the same target column. The in-database algorithm then builds an ensemble model composed of multiple submodels, one for each partition of the data. The goal is to see if we can achieve better accuracy through multiple targeted models that are managed and used as a single model. And these submodels are presented as a single model to the user. This simplifies model management, deployment, and scoring by allowing the user to just work with that top-level model. So partition models are supported across SQL, R, and Python APIs with the in-database algorithms. And here we're showing using the SQL API for building such a partition model. The key specification is highlighted where we have the ODMS partition columns indicate the column or columns that we want to partition by. And the other specifications remain the same for the model building. Users can explore the model details of each submodel explicitly, as we're showing here in the output below. And scoring is done, as we showed in the previous slides, whether you're using SQL, Python, or R interfaces. So we've seen a number of automation features from the OML AutoML UI, OML for Pi, AutoML, and the core in-database algorithms. So when it comes to modeling and deployment, there are multiple ways to produce and consume models using OML. Here, the AutoML UI, once an experiment has produced the desired results, one or more of these models can be deployed to OML services. And this allows them to be used by custom applications, including those that are based on Oracle Apex. And this leverages REST endpoints. Now, models produced by the AutoML UI can, of course, be used directly in SQL queries for scoring from applications. And those same models are available within Oracle Analytics Cloud. And these leverage OAC's integration with OML for both scoring and visualization. And as we showed earlier, users can generate a notebook for selecting for the model they've selected, and also customize the generated Python code, and then run that notebook to build a model. The resulting in-database model can be exported and deployed to OML services for use by applications, or it can also be used immediately from SQL. Now, using OML notebooks, users can leverage OML for Pi's AutoML to build models programmatically, or the individual algorithm modeling API to build models manually. And OML notebooks provide similar options for deployment through OML services and use with Oracle Analytics Cloud. Now, one thing you might not be aware of is that models produced in the cloud on autonomous database can be exported and deployed in other autonomous databases, as well as on-premises Oracle databases. Similarly, you can build models on-premises and deploy them to autonomous database. So OML offers flexibility to operate across cloud and on-premises environments. So to wrap up our discussion, just a quick summary of the Oracle Machine Learning family of products that supports data science projects. Oracle Machine Learning provides interfaces for 3 popular languages, as we've been talking about, SQL, R, and Python. OML for SQL exists in all the database versions and platforms. OML for R is currently supported for on-premises databases and Database Cloud Service. And OML for Pi is supported on Autonomous Database and on-premises 21c Oracle database. Now, for interaction with the Autonomous Database, we provide OML notebooks. This is based on Apache Zeppelin, and it supports SQL, PL/SQL, Python, and Markdown interpreters. And what's nice about this is that the same notebook can contain both SQL and Python paragraphs, allowing users to choose the most effective language for the task. Users can version notebooks as well as schedule notebooks to run. Oracle Data Miner, as some of you may be familiar with, is a SQL developer extension that enables users to create, schedule, and deploy analytical workflows through a drag and drop user interface. And this is compatible with on-premises and Database Cloud Service databases. Oracle Machine Learning for Spark provides machine learning in the big data environment, such as Big Data Service with native scalable algorithms, as well as Spark MLlib algorithms that are included in the same framework. And as we discussed earlier, we have Oracle Machine Learning Automl Ui, the no-code user interface for automating the model building, selection, and deployment process, and Oracle Machine Learning Services, this RESTful service for model deployment and management, along with cognitive text analytics. So users can deploy a model from the AutoML UI directly to OML services in just a few clicks, as we demonstrated earlier. So if you'd like to learn more about Oracle Machine Learning, check out on o.com, our machine-learning site, as well as we have live labs where you can quickly spin up an autonomous database and work through various scenarios using OML technology. And included with OML notebooks on Autonomous Database are a whole set of template examples for our SQL and Python interfaces. Examples are also provided in the Machine Learning GitHub repository, and this will include notebooks, but also scripts that you can use with our R and SQL interfaces, among other tools. And lastly, through our OML office hours, you'll find a rich library of recorded sessions with product demonstrations, use cases, and application integrations. So you can sign up there to receive notifications of new sessions. So thanks. I hope you enjoyed today's session, and happy to take any questions that we have time for.
Hey, Mark, that was amazing as always. Thank you very much. Really appreciate
My pleasure.
it. You've got 2 questions, so I'll read them out for you, and maybe we can have a bit of a discussion. So how does Oracle AutoML handle data imbalance and bias issues?
Well, in terms of the data imbalance, that is one of the key phases for the AutoML UI, right? There is actually a place in one of the stages in the process that looks at the imbalance and will do stratified sampling as appropriate to correct for that to the extent that's possible with that. So it is taken into account.
Cool. And David also asked the second question, which is, it seems Oracle AutoML deals with supervised learning. Which tools does Oracle provide for unsupervised learning, such as clustering and anomaly detection?
Excellent question. So we have a wide range of machine learning techniques that are provided in the tool itself. With the AutoML, today we're supporting classification and regression, but we are planning to expand into other areas there, but I'm going to keep those under wraps for the time being. But certainly in the broader product, you have access to clustering, association rules, feature extraction, time series. So there's quite a range of machine learning techniques that you can leverage directly through the SQL, R, and Python APIs, including Oracle Data Miner as well.
Phil's just asked one on the chat, actually, which is really interesting. Is the technology going to be integrated with Graph, so GraphML?
So you know that Oracle has this converged database technology and this concept of bringing all of these different types of specialized analytics together in the single converged Oracle database. And so We have spatial and graph there. We have machine learning. We've got blockchain and a number of other technologies. And in the past, we had looked at how can we facilitate this exchange between machine learning and graph analytics. And one of the things that we did was to say, well, we want to be able to have data be scored from machine learning as adding value there, and then feeding those into the graph representation. And so the graph capability can take tabular data now and incorporate that into a graph structure. And then we can also compute graph metrics on that and export those results as tables that can then be immediately fed back into the machine learning process. And so we really have this great symbiosis through the database, if you will, that allows us to go back and forth between these two technologies and leverage that. There are, I believe there's a Python API for graph as well that's available. And so that further, supports this way of working through Python for the machine learning side, as well as with the graph technology.
Interestingly, I was working with the graph people yesterday on the graph day, TechCast demo days, and a lot of what you're saying was actually demonstrated there. So if people are interested in getting more detail on that, once the recordings are posted from yesterday, those could be very useful to you. And also those presentations will, if you like, expand on what Mark has just been saying in his answer to that question.
Great.
That's it, Mark. You've just got the 3 today. That was
all right.
You covered it all, my friend.
Yeah, Mark, I was saying to Abby in the background that your brain must actually have, it's like everything must be in neat, orderly boxes, like a library or something. The way you present is so methodical and ordered. It's lovely to listen to. Thank you.
Well, I hope you got something out of it. I appreciate the feedback.
Yeah, no, it was very good. Thank you.
Thank you. Okay.